All right, everybody, let's get started. Let's see, are we recording? I don't want that part. Let's see. Yep, we're recording. Let me minimize this. Let's get started. Okay, so right off the bat, I will admit, I know I got a lot of emails on Thursday because of the weather. There was a lot of you that were snowed in. I did account for that when I took care of the attendance, so but if I didn't respond to you, I'm still digging myself out of the email hole, so I will. But rest assured that if you were supposed to be excused on the last lecture, that you were. So the attendance grades are up to date. So as of now, for the homeworks, let's talk a little bit about that. So homeworks 1.1 and 1.2 are graded. You submitted 1.3 this morning, or it should have been done by this morning. That was the last homework that set up like the quiz where you enter the values. From here on out, we're going to do the homeworks how we did them in statics last semester, where you scan and upload the PDF, because I think that's probably what everybody's kind of used to. I'll go ahead and tell you the reason for the initial assignments, and we actually did this in statics last semester as well, is honestly I just needed a little bit of time to get my TA set up and get them in the system and get their hiring paperwork done and whatnot. And once they were in, it's like, okay, now we can do it the way we normally did it. So with the weather and whatnot, that was delayed a little bit longer than I would have liked. But we're back into the normal swing of things. All right, so what we're going to do today is dispense with the fundamental stuff that we've been talking about for the last few lectures and actually get into some real deal problems. So the way that mechanics of materials works, and forgive me, I'm probably going to use the term mechanics of materials instead of mechanics of deformable bodies. I mean, it's literally the title of your textbook. Is that once you've introduced the concepts of stress and strain, you then start applying them towards classical problems in engineering mechanics. And so we're going to begin with the first type of problem that we tend to deal with in this science, which is axially loaded members. And so we've kind of already talked a little bit about axial loads because we use that to introduce the concepts of stresses and strains. But now we're really going to take a look at some practical applications. So just to make sure that everybody's clear, what we've done for the past 3 lectures is really introduce sort of 3 concepts. So the first is the definition of stress. So the idea that instead of dealing with forces, we deal with forces per unit area in order to assess engineering performance. So it's sort of a normalized description of force. We then introduce the concept of strain, the idea that strain is not a measure of deformation, but sort of a rate of change of deformation, a deformation per unit length. And so if stress is a concept and strain is a concept, the third concept is that stresses and strains are related for given materials. So if you know what material that you're dealing with, you can relate the applied stress to the resulting strain. Okay? And so we're going to use these relationships, the relationship of stress and strain along with those definitions, to essentially start looking at engineering problems. And so the very first one that we're going to look at is an axially loaded element. And so to be clear, the way that this course works, I am not going to teach you how to analyze or design a bridge. I'm not going to teach you how to analyze or design a car frame or whatnot. Instead, what we're going to do is look at various components of these types of systems. Elements that are being applied with axial load, elements that are being twisted, elements that are being bent. Because if you're looking at a bridge or a car frame or what have you, what do you think they're composed of? They're composed of elements that are being bent, elements that are being twisted, elements that are being loaded axially, etc. And so all of the engineering systems that we tend to deal with are comprised of these components. That's kind of why we focus on this the way that we do. Now, what we're going to try and do with these components is sort of relate the beginning and the end of the picture. So if I have an axially loaded bar, I'm taking a bar and I'm yanking on it or I'm compressing it. So here's a bar and I'm applying some, let's say, tensile load. I propose that, okay, so we'll use this pencil. So here's this pencil. I take this pencil and I apply a tensile load. I yank on it. I propose that as I'm yanking on it, it elongates. So how do I compute that elongation? Well, what I can do is I can, and basically what you're doing is connecting the 3 concepts. If I apply the load, I can compute the stress. If I know the material properties of the pencil, I can compute the strain. And if I know how long the pencil is, I can take that strain and compute a displacement, right? Well, what we can also do is relate all of that in one big equation. So that's what we're going to do. So let's just break it down a little bit. So these three gray boxes right here are essentially the three concepts that we've been defining for these first few lectures. So, right now we've been using, for instance, concepts in equilibrium and cross-sectional properties to turn forces into stresses. And then we use compatibility relationships to turn deformations into strains. And then we can relate stresses and strains with material properties, with constitutive properties, such as the Young's modulus. So, for example, how can we lump all of this into one expression? Well, let's take a look at this equation right here. Okay, so stress equals E times the strain. Well, what is stress? Well, stress can be defined as P over A. So right here, instead of stress, I'll use P over A. What about strain? Well, instead of strain, deformation per unit length. Solve for delta, so divide both sides by E, multiply both sides by L, boom. There you go. I propose that if you have a pencil, like this pencil, this axially loaded element, take this element and yank on it with some force P. The pencil is some length L, it has some material properties E, some cross-sectional area A. I can compute the displacement pretty easily. Delta equals PL over EA. Simple, right? Well, for the most part, yeah, it is simple. But there is an added wrinkle that we need to throw into the situation. And that is, this equation assumes that everything is constant. Okay? Now, some of those make sense. For example, very rarely would I ever have an engineering system where the Young's modulus appreciably changed from one side of the element to another. In other words, if I'm looking at a strut in a car frame, or if I'm looking at an element in a truss, I can pretty much assume that that element is steel throughout, so I can use the same E value throughout. But it is very possible that some of the cross-sectional properties change along the length. For example, how about this bar right here? Here's an axially loaded bar, and the area changes across the length. It gets bigger as it goes down. This type of system is used all the time in engineering systems. So how do we handle that? Well, we break out our old friend calculus. And instead of looking at this from a just constant plug and chug expression, we might need to integrate. Okay? I propose that in the types of problems that we deal with in engineering, really the two components that might vary is the load or the area. So instead of a constant load and a constant area, I propose that the load and the area might vary as a function of x. And so in order to determine the deformation, I might need to integrate. I might need to integrate this N over EA in terms of x. Now, just so you are aware, if these terms are constant, right? So let's say you do have a constant load and a constant area. What happens? Well, let's go back to Calc 1. If I have what's the integral of a constant, right? I can factor that out, and what's the integral of dx? It's just x, right? X evaluated from 0 to L, plug and chug, and you will get this same formula. So this integral, this infinitesimal expression of deformation, will still work if the components are constant. But if they're not constant, this is going to be a little bit more usable for us as engineers. And again, to be clear, I don't want to be that guy who's just throwing calculus out because calculus is fun. I'm going to show you two examples where it's actually necessary to use these components in the real world. Okay? Any questions about what I'm setting up here? Any thoughts? Anything that's confusing? So again, all I'm doing here is, if everything's constant, just PL over EA. If it's variable, what I'm doing is I'm looking at the displacement in a little element, so load times the length over EA, the length being that infinitesimal length dx, and I'm just summing those up. I'm integrating. Okay? Any questions? All right, so let me give you two examples. I'm going to give you one where the load varies and one where the area varies. So the area varies, I think that's pretty simple. I think that makes sense. The rod is getting bigger, so we can't just use PL over EA. We also can't really use an average area. I mean, we could, but it's not going to be correct. Actually, integrating that is going to be the appropriate approach. But this one right here is, it may be a little deceptive that the load varies, but let's take a look at the problem description a little bit. So I have a bar here that's hanging off a support, and it is subjected to an axial load here, but here's the kicker. In addition to its own self-weight. All right? Now, how many of you have ever seen or held a 2x4? Okay, all right. So imagine I had a 2x4 right here in my hand that was a few feet long. I could probably hold that up with my bare hands, right? Now imagine if I had a 2x4 that was 2,000 feet long. You think I could just hold that up like that? Or is that going to be... Did you say probably?
Yeah, I've got pretty high hopes.
You got, yeah. I promise I'm not from Krypton or anything, so I don't think I can do that. Although I appreciate the compliment.
Thank you.
But in all seriousness, the 2x4 gets heavier as it gets longer, right? So its load varies as a function of its length. Does that make sense? Everybody okay with that? Okay. If that concept makes sense, there is only one thing I want to clarify, and that's units. What is the modulus of elasticity reported for this problem? What does it say? 12 times 10 to the 6th what? Now hold on, what is PSI? Pounds per what? Okay. How long is the bar? Wait, what? The modulus of elasticity is in PSI and the bar length is in feet? What do I do there?
Multiply feet times 12 and you get 600.
There you go.
If I did that math right.
You did.
Thank you.
Here's my point, okay? And this is not an exclusively U.S. customary units problem, okay? You are going to deal with problems, not just in this class, but in engineering systems in general, where the units don't coincide. Let's deal in metric plan. Let's deal in metric plan. If I wanted to describe how wide this room is, what units would you use in metric? Meters, probably. That probably is a common unit for how wide this is or how long this room is. Now, what if I asked you to compute how much this beam deflects in the roof? We're talking about deflections like this. Millimeters. So they're already different unit systems. Now, you could argue that the unit conversions are easier because they're in factors of 10. Okay, that's fine. But you still have to do them, right? That's going to happen in this course. And I'm going to tell you right off the bat, that is a problem that is much more prescient in this course than it was in statics. In statics, we were just dealing with sum of forces and everything was pretty much in the same unit system anyways. But because we're dealing with normalized expression of force, normalized expressions of deformations, we're going to have unit mix-ups and you kind of need to be aware of it. My rule of thumb is just convert everything to a consistent unit system at the beginning and let the math take care of the rest. Everybody good? All right. Let's do this one. Okay. Okay. So what we're going to do is we're going to sort of restate some of these parameters right off the bat. Let's just make sure that we're all sort of on the same page. All right. So too soon? That was a joke.
Oh. Yeah, you're already losing points.
Given parameters.
Where you're done.
We're going to do problem parameters. I'll accommodate.
You didn't date.
You didn't label it.
No,
Oh.
that's
You didn't
happening.
name
You already
it.
have
It should be Michael.
Yeah.
Yeah.
You gotta start.
Now everybody's awake at 8 o'clock in the morning. Now I get the secret. Okay. All right. So, all right. Modulus of elasticity. What's the symbol we've been using for that? E, right? So E is, in this case, 12 million psi. Which, by the way, if you've, how many of you have a calculator that has like normal scientific mode and then engineering mode for the numbers? How many of you have a calculator that does that?
So to the power of 3.
That's what engineering notation does. It's basically scientific notation, but it does the exponents in terms of 3 because we, like for example in metric, we might deal with kilonewtons or newtons or meters or millimeters. And so a lot of times in engineering computations, we deal with things in factors of 3. Even in US units, we have pounds, we have kips, you know. For example, we have like strains and then we have microstrains that we deal with times 10 to the 6. So that's why. So, okay. All right, the length is, in this case, 50 feet. But go ahead right now, okay, right now and say 12 inches per foot and say 600 inches. Just do it right now. Don't avoid it, just do it now. Okay? Now, we've been given another term, the yield stress. Okay, we're going to look at that here in a second, okay? So, oh my goodness. Okay, now we were given also a bar weight. Now let's make sure everybody's paying attention. So 0.818 pounds per foot. Now I need to convert that, if we're agreeing with pounds and inches, I need to convert that to inches. How do I do that?
Divide by 12.
Divide by 12. You don't multiply by 12, you divide by 12. Because it's just think about it in common sense terms. If something weighs like 100 pounds per foot, it only weighs, 8 or so pounds per inch, right? So think about, the concept. We're dividing by 12. So this is, I like to do my unit conversions in green. So I get 0.06817. Can somebody second me on that? After the algebra hiccups that we had last time, I want to make sure I got that right. Okay. All right. And then we have the bar diameter, which is 0.5 inches. Okay. And by the way, if I'm scrolling too fast, same story with statics, just let me know. Don't hesitate to stop and go, what the heck are you talking about, Dr. Mike? Okay. So the problem is asking for two things. So the first thing that it's asking for is the load required to initiate yielding. Okay? And specifically what it's talking about is it's talking about this load Q. Okay? So here's the bar, and it's asking how much force here, how much Q is required to cause yielding. Okay? So here's what I'm going to do. All right? We know the yield stress. Okay? So let me just ignore the problem for the fact that the bar is hanging upside down, etc. Let me ask you this. We have a 1/2 inch diameter bar, and we know that it will yield at 20,000 psi. How would I determine how much force is required to yield the bar? Yes?
Multiplied by area.
Exactly right. Multiply by the area. So let's title this Q required to initiate yielding. Can everybody read that in the back? Is that good? Okay. All right. So we need the area, which how do I determine the area of a circle that's half-inch diameter? I would say, there we go, pi over 4. Okay, and I think I can do that one, 0.196 inches squared. I get that right? All right. And so what you said, which was 100% correct, is to multiply that times the yield stress. Okay? So I'm going to call that Py. So I'm going to say Py is sigma y times the area, which is 20,000 psi times 0.196 square inches. Somebody with a Casio FX115 ES Plus or similar scientific calculator, I know it's 8 o'clock in the morning, but everybody got all woken up with these parameters. That means you're awake enough to do some of these computations for me. So what is that?
3,920.
There we go. All right. So I think I got like 3927, but it doesn't matter. 3927. Everybody's sort of on the same page. And that's pounds, right? I kind of glossed over that, but we're talking about a force. Pounds per square inch times square inches. So is that the value of Q? Now you're shaking your head no. Why?
You have to subtract the total weight of the bar.
Exactly, because the bar currently has a load on it, on top of Q, its own self-weight. So how would I determine how much load is on it in terms of its self-weight? We know the bar weighs 0.06817 pounds per inch. We also know the bar is 600 inches long, right? So what we need to do is subtract that effect out. So Q is Py minus, we'll call it the bar weight, which is, here, I'll do it like this. Minus the effect of the weight. And think, the longer the bar is, the less load, the less applied load it's going to take to yield it. Because the longer the bar is, the more that self-weight is going to contribute towards potential yielding. Does that make sense? So what are we getting here for this value? What are we getting for Q? We'll say to the nearest pound. 3886. Do I have a second on that? There we go. So there you go. That's the answer. So we're not getting, too much of an impact from the self-weight, but again, the longer that bar is, the more impact we're getting. What'd you say?
The letters over on the left. You gotta make sure you get that checked.
Where Q equals.
What?
You know what? You're wrong. You're just wrong.
That answer doesn't look good. You wasn't given parameters. You also plugged in values earlier.
I award you no points.
Not the matter with it, I swear.
Yes, sir.
What is the subscript that you have at the beginning, like D subscript squared? I can't tell what that is.
Oh, right here,
Yes.
bar, for the diameter of the bar.
Okay.
Yeah. I was suddenly reminded of like the moderator's response on Billy Madison after the question? Like, what you have just said. It just felt like actually just a simple wrong would have sufficed. All right. Okay. Hold on. Settle down for a second. Does anybody have any questions about this part so far? Okay. Now, what we're now going to ask is the second part of this question, which is, okay, let's say we put 3886 on this bar. And let's assume for the sake of discussion that it's still behaving linearly. What is the deflection under that load? Okay. So now let's assess that. Okay. So here, I'm going to scroll down a little bit. All right. So here's the bar, and the free body diagram indicates that there is a load Q applied at the tip. But this isn't enough. This isn't enough to fully encapsulate the load applied to this system. See, I propose there is another load applied acting downward, W of X. And I propose that the longer the bar is, the more that load, the more magnitude of load that's present. See, if I cut a section using a samurai sword or lightsaber, if I'm a sci-fi fan, and here's my section cut, what I'm trying to determine is that normal force as a function of x. Okay? So I mean that this dimension, we'll call this x. And I propose that that self-weight that's being applied equals W bar times x. I mean, isn't that what we did up here? I mean, up here what we said was, in order to compute Q, we're going to take the yield load minus the bar weight. And how did we determine the force from the bar weight? We took this 0.6817 and we multiplied it by the length of the bar. So I propose that the axial load inside the bar from the self-weight is equal to the weight of the bar per unit length times whatever length of the bar that we're considering. If the bar length is 3 inches long, well, we're only dealing with this much force. If the bar length is 692 inches long, we're dealing with that much force. Does that make sense? So I propose that if we sum forces in the y direction, remember this? So nx going up, minus q going down, minus that going down is 0. Oh, hold on. That's a P, not a B. Does that make sense? That the axial load is variable as a function of x? The longer the bar is, the heavier it is. And it's just weight per foot or weight per inch times the length. Everybody with me so far? So now we're going to get into calculus land. My apologies, but we are. but I want to show you something. Okay? All right. So here's what I propose. So the total deflection, that's the lowercase delta, is instead of PL over EA, we're going to integrate from x equals 0 to x equals L, n over x divided by E A over x dx. Okay, this is our expression. Now this expression is set up to be able to handle both variable loads and variable area. Do we have a variable area for this problem? No. Okay? So A is a constant. Okay? But this is a function. Okay, this is a function. Okay? So this is going to be integral from x equals 0 to x equals L of it's going to be that. Go away. Now, if I remember correctly, so now we're in calculus land. Okay? The variable is x. Everything else is a number. Okay? Q is a number. E is a number. A is a number. W is a number. So let's break out some tricks that we learned in Math 229. So an integral of a sum can be split up as the sum of integrals, right? So what I can do is say, all right, we can do that, right? I can take these constant terms, factor them out of the integrals, but before I do, I want to just illustrate something. I want to look at these two integrals, okay? This integral, the load, hold on. Is constant. The load is variable. Why is that important? I want you to pay attention to this integral on the left and see what happens. Okay? So everything that's inside the integral on the left is a constant, right? So I can factor out the Q, the E, the A, etc., and I'm going to get this. And over here, the integral has that pesky little x left over. Now let's pay attention to this integral over here. What is the integral of dx? X. Okay? So this is x evaluated from x equals 0 to x equals L plus what about this one? What's the integral of x? No.
X squared over 2.
X squared over 2. Now, we're also not doing the plus c because it's a definite integral, right? So a definite integral, we plug in the top number minus plug in the bottom number. Zero. All right. Now, you might be wondering, why the heck does he keep writing these x equals zeros and x equals l's? Like, why doesn't he just write 0 and L? It'll come clear. Bear with me. Basically, you'll see why on the next problem. But I got my reasons. Trust me. Now, over here on this left integral, we plug in the top number minus plug in the bottom number. Over here, I'm going to be lazy and factor out the 2EA and plug in the top number minus plug in the bottom number. What do I get here on the left? I get QL over EA plus W bar L squared over 2EA. So, before we start plugging and chugging, look at this. What happened over here on that integral on the left? The integral on the left, we had a constant load and a constant area. So what did it reduce to? PL over EA, right? It's just Q instead of P, but it's the same formula. For the integral on the right contained the variable component. So that PL over EA formula doesn't work over here because the load changes as a function of length, so we get a different expression. Okay. The other thing I will mention is that, I don't want to get too far down this rabbit hole. This is not a calculus course. We are using calculus, but I'm not going to have integrals of the tangent of fourth e to the pi x dx. That's not what we're here to do, okay? If there are integrals that we need to perform, they are going to be basic, but necessary, okay? So, everybody okay with that? I'm not going to turn this into a relitigation of Math 230 or anything, so. Okay, all right. So, now we can start plugging and chugging. So, why does this thing keep popping up? All right, so, therefore, delta equals, okay, so let's look at this first fraction. So this first fraction, 12 million psi, the area is 0.196 square inches, and then Q is 3886 pounds times the length, which is 600 inches. Okay, so I apologize if that's too small in the back. If you need me to blow that up, I will. But this is QL over EA plus, then we have another fraction, 2, don't forget the 2. And this is 600 inches squared. So, over here on this second formula, don't forget the squared, don't forget the 2. That could have been bad. It wasn't, but it could have been. If everybody's wondering, I almost slipped on this stair right here. So what do we got here for this one? I usually like to do my deflections to like 3 decimal places. And we might get some slight differences with rounding and whatnot, so that's okay. I'm not too worried about that. Everybody got an answer for me? Anybody? Okay. Okay. Do I have a second on that? That's what I got. 0.9. I got 995, but 996 is close enough. So that we're clear, what are the units for this? Inches. We're computing a displacement. So if you want, the easiest way to look at the units is to look at this fraction over here. If we look at the bottom, pounds per square inch times inches squared will yield pounds. So pounds on the bottom, pounds times inches on the top, the pounds cancel and I'm left with inches. You'll come to the same conclusion over here as well. So this is in inches. If you are not getting this answer, I would check your computations and make sure that you're comfortable with this. This is not that unheard of in terms of the complexity of formulas that we deal with in this course. This is actually pretty on par. So make sure that you're comfortable with this, level of complexity in your computations. It's not like statics, where with statics, I mean, yeah, there were some cross products and whatnot, but when it came to like summing forces, you were just adding stuff up. So with this, there's a little bit more going on the units and the math. Any questions? Okay. Do I need to leave this up for a little bit? Okay. Okay, let's look at this one. I like this one. So, this one's a little bit different, okay? Now, in the interest of brevity, I'm not going to repeat all of the system parameters or problem parameters or whatnot, because they're all already listed here. I have also taken the liberty, other than the E value, to convert everything to consistent units, which we'll do this here in a bit. Which, by the way, we can handle this one of two ways. It doesn't really matter. We can either take the P and turn it into 25,000 pounds, or we can take the E and turn it into 30,000 KSI. Either one's fine. The thing about this problem, though, is I do not have a variable load. I have a variable area. I have a tapered bar. So the bar is getting bigger as you go down the length. So, like with the last problem, we are going to have to integrate. Okay? What we're going to have to do is we're going to have to develop an area function, an area as a function of x, and then perform a similar integration. Okay? Does this make sense? All right. I am going to test you a little bit on your calculus rules, but this will be the farthest. I'll go ahead and tell you that on your homework assignment, the calculus stretching, if you will, we've kind of already done some of it. So in lecture. In other words, this is harder than what you're going to have to do on homework. So don't worry about that. Okay. So let's make this kind of simple. Let's reason through this thing. Would you agree that if I samurai sworded or lightsabered through this bar, doesn't matter where, the cross section is going to look like a rectangle? Like, whether or not I cut here or here or here or here, doesn't matter, it's a rectangle. It's just that the area of that rectangle changes. Now, how do you compute the area of a rectangle? Just basic. Well, just a box, the length times the width, right? Or the width times the thickness. We're not talking about volume, just area.
You were there.
When you integrate with a triangle on top of the rectangle and the triangle separate, right?
What?
Yeah, for that shape.
Well, if we're
right?
If we're trying to determine the area of this, I'm not trying to determine the area of this. I'm trying to samurai sword or lightsaber and determine the area of the cross section. The area of the cross section is just a rectangle.
Yeah.
It's just width times thickness.
He's trying to save himself because he thinks he sounds dumb.
No, but like, when you add up the area, don't you do it like an integration with respect to L and just add like the?
Well, we're getting there,
Okay.
but we're not interested in computing volumes though.
Yes, that's your delta X.
Oh,
That's what
okay.
you're at.
I get what you're saying, but we're not quite interested in that. So,
Okay.
here's my point. Would you agree that the area of this rectangle is B times the thickness, right? It's just that the B changes, right? Like over here, the B is 4 inches, and over here, the B is 6 inches. You okay with that? So all we need really is the width as a function of x. And all we take that width and multiply by the thickness, we get the area. And by the way, what's the thickness? 1, right? Everybody with me on that? So let's keep this simple. So let's call this x is 0. Let's call this x is L. Now what is L for this problem? 60 inches. So would you agree with this? Would you agree that at x equals 0, the width is 4, and at x equals 60, the width is 6. Would you agree with that? So, does it look like the area is or the width is very linearly? It's a line, isn't it? They're varying linearly. So, maybe what we've got are 2 points, 0, 4, and 60, 6. Do you all know how to find the equation of a line with 2 points? Maybe what we should do is first determine the slope, which is in this case going to be the change in B over the change in X, which is right? And the intercept is 4, right? Because at x equals 0, the function equals 4. So would you agree that b of x is 1 over 30x plus 4? And the area is going to be b of x times the thickness. And since the thickness is 1 inch, is that right? Sounds right to me, doesn't it? You're shaking your head no.
Forgot to box the letters on the left again. That's 3 points off.
You know what?
You got a 25% on this question. Congratulations.
Oh my goodness.
Some people would tell you need to reevaluate. Yeah.
Would you
I got a PhD and I've been a professor for 8 years. Yeah, I don't know what's going on.
Would you have turned that into your employer?
Yeah, would you?
I think not.
They hire you
My
for that.
dearest student.
Did you at least get the class name right?
Let's stop this and go back to the formal. Okay, all right. So what we're doing here is we are integrating I mean, we're going to start with our, starting expression. This is what we're going to start with, okay? Now, what's different about this problem is that before we had a variable load and then we had a constant area. Now we're kind of flipped, okay? Because I want to make sure that we're clear on that. Here's the bar, okay? It does not matter where I samurai sword or lightsaber through the bar. The bar has a constant axial load of P, right? There is a 25 kip axial load inside the bar along all points, right? So P is constant. It is the area that's variable. Now, could we have a scenario where both are variable? Yeah. Imagine if I took this bar and considered it self-weight acting up and down. Then you have a constant load and a constant area. I don't think that that makes the problem more intellectually challenging. It just becomes more of a calculus problem, so we can do it, but I'm interested in you learning the concept, so we'll move past that. But for this problem, we have this. We have P, E, but now we have 130x plus 4. And what we'll do is we'll say P dx. Now, what I'm going to do is I'm going to factor out the constant terms P and E. And I'm left with this. Okay, and what I'll also do is, let's just leave it like this. Let's just leave it like that. Okay, now like I said, this is as far down the calculus rabbit hole as I think we're going to go in this course in general. But I need to be able to evaluate this integral. Now, if you remember those integral formulas that can plug and chug, fine. I'm not that good. I can't remember that stuff. So what I'm going to do is do some substitution. Okay? What is the derivative of that? So du is 1 over 30 dx. dx is 30 du, right? So we'll look at that. Look at that. And then we'll say P over E integral x equals 0, x equals L of 30 du over u. Now notice, so if you were wondering in the last problem, why is he writing the x equals 0 here and the x equals L here? Because I didn't bother to convert these. I could have, but I'm going to back substitute later anyways. So I'm leaving my integration limits in terms of x, but the inside of my integral in terms of u, because I'll change that here in a little bit. So what we're going to do is we're going to say, all right, now we need to integrate this. So if I factor out the 30, I have the integral of du over u. Does anybody remember what the integral of 1 over x is, or du over u?
Natural log.
The natural log, right. So now what we're going to have is we're going to have 30p over e, right? Let me scroll down, because I'm crouching here a little bit. So now what we're going to have is the natural log of u, evaluated from x equals 0 to x equals L. But what I'll do is now I'll just resubstitute. Is this making sense? Okay, so what is L? Hold on, let's recall. What's L? Thank you. L is 60. So 30p over E. So Ln right? Plug in the top number, which is 60. So 60 over 30 plus 4 minus plug in the bottom number, right? So I've got now let's just, for fun, if you have the natural log of 6 minus the natural log of 4, do you remember how you can collect that? There you go, natural log of 6 over 4. So this is going to be 30p over E natural log of 6 over 4. Now notice, I've been a little fast and loose with documenting my units, but it doesn't really matter all that much because I can convert to consistent units at the beginning. Now, the one thing we didn't do is decide whether or not we wanted to convert E to KSI or P to pounds, because we've got, let's recall this up here, because we were given that P is 25 kits, and E is 30 million PSI. What I'm going to do is say that that's 30,000. Ooh, I don't know what happened there. KSI. So now when I plug in P and E, I'm just going to use 25 and 30,000. So therefore, the deflection is 30 times 25 times the natural log of 6 over 4 over 30,000. This answer is a little bit smaller than the last one. It's a lot tinier. And one of the reasons it's tinier is because if you look at the material, look at the loads, and look at the size, we just have a really big bar made of a very high quality material that's really not being subjected to a lot of load in the scale of engineering applications, so it's just not that much. Yes, sir?
How many get the
Say 4.
0.0101.
There you go, yeah. This one's tiny, yeah. And these values, these types of numbers, aren't that unheard of. And in some cases are desirable and necessary. You're talking about elements that require a lot of precision. Sometimes you don't want a lot of deformation. So you need to use a high quality material and a beefy section in order to prevent that from happening, Just depends on the application. In some engineering applications, that might be too much. You might actually need to beef it up, if we're talking about machine precision and whatnot. In some applications like bridges, I might say that's over-designed. You can back that bar down a little bit. It's okay to have a little bit of deflection. It just depends. Depends on what you're doing. So, any questions? All right, I want to give you a taste of things to come for the next couple of lectures. So, and I want to talk a little bit about the homework, because I don't want to throw you to the wolves, if you will. So, first off, let me talk a little bit about the homework. The homework focuses on a particular problem in the textbook. It's textbook problem 2.3-11. And in that problem, I'll go ahead and tell you, so basically what you're given is a stepped bar, okay? And you have to compute the total elongation, And so one of the things I want to clarify for you to help with that homework assignment is that, remember, we've got a constant formula and a variable formula. And the variable formula involves an integral. Right? What are you doing when you compute an integral? It's just a sum, right? That's basically what an integral is. Okay? So what I'll tell you is that in this homework assignment, what you're given is essentially a problem that looks like this. So the problem looks something like this. I keep hitting this mouse button. That's probably going to happen a lot this semester. So the problem looks something like this. Right? And the loads, whatever these loads are, don't really matter. Let's say they're like, I don't know, 15 kips. I don't remember what they were. I did the solution last week. So if you wanted to find the total elongation, what you would be doing for a problem like this is, if we call this part right here bar 1 and call this bar 2, what you're going to be doing is the deflection of bar 1 plus the deflection of bar 2. And that could be P1 L1 over E1 A1 plus P2 L2 over E2 A2. Okay, that could be the way that you do it, right? One part of the problem says, okay, let's take this load and turn it into a distributed load. Let's distribute it over the length. So maybe this remains a constant, and this one you need to integrate. Okay, so you're gonna have scenarios where you might need to do that. What I'm getting at is that whenever you have a scenario where you have not a bar, but a sequence of bars, just sum up the deflection formulas, the PL over EA for this bar, the PL over EA for this bar, and sum them up. So all you have to do essentially is, look at each bar, compute its properties, look at it from a statics perspective, etc. Now, part B of the problem says, okay, we have a stepped bar. What would the deflection be if it was just a prismatic bar, if it was just a single bar of uniform cross-section? But the kicker is that the prismatic bar has to have the same volume. So what I would do is compute the volume of this, and then ask yourself, well, what does the diameter need to be of a single bar to have that same volume? Okay, and I put that in a hint on the homework assignment. I said that for part B, first compute the volume of the entire bar, then compute the cross-sectional area required for an 8-foot long bar, to generate an 8-foot long bar of equal volume. Okay, because I think that's a good mental exercise, but I wanted to give you a hint to try and help you out on that. And for part C, don't forget consistent units. So I got a couple other things I want to mention before we close it, but does anybody have any questions? What'd you say? Sure. And to be clear, there is a part of the problem, I want to be crystal clear, there is a part of the problem where one of these forces is converted to a distributed load. So one of these, instead of this constant formula, you might need to integrate for a later part of the problem. So that's all I'm saying. Any other questions? So I got two other things I want to say, and then we'll call it. All right, so we have 2 more lectures on axially loaded bars before we move on to our next topic. So I want to give you a little bit of a taste of what's to come in your next couple lectures. So one of the things that mechanics of deformable bodies gives us that statics did not is the ability to handle problems that are indeterminate. Okay? We talked about this a little bit in statics last semester, the idea that some problems might have one too many unknowns. That statics isn't enough, right? And so mechanics of deformable bodies gives us the ability to handle problems of static indeterminacy. And it does so because we must respect the compatibility of the resulting deformations. I'll give you 2 examples that we're going to deal with next time. So I can very easily compute the stresses, strains, deformations, etc. of a single axially loaded bar. But what if I had a composite axially loaded bar? What if I had, let's say, for you civils, what if it was a reinforced concrete column? So it was concrete with steel inside it. So now it's 2 materials. What if it's a brass shaft that's sheathed in an aluminum pipe, and I load it? How much load goes to the aluminum? How much load goes to the brass? Those are real issues that you would have to deal with as civil or mechanical engineers. The other is the concept of external indeterminacy. What if you have one too many supports? Well, the way that you handle that is through mechanics of deformable bodies, because the deformations have to be consistent. Okay? And that's what we're going to deal with on Thursday. On next Tuesday, we are going to deal with something which is probably seems more near and dear to the mechanical engineers, but has some civil applications as well, and that's thermal stresses and strains. What if you take a bar and you heat it up? Well, it gets longer, right? So, how does that result in thermal stresses and strains in concert with mechanical loads and whatnot? We're going to be able to discuss that on Tuesday. But that's what's coming for the next couple days. Any questions? I think we're ending a few minutes early. Enjoy the extra time between now and dynamics. I will see you all on Thursday.